starting with temperature from A levels. First, we need to understand that energy is transferred from a high temperature region towards a low temperature region. Basically, this is talking about infrared radiation or energy that is detectable or convertible or transferable by conduction convection as well. So when do you see, or what would be a real life example of thermal equilibrium? For example, you bring in a cup of coffee or a cup of tea, for example, in your room, and you let it rest in your room for a while. And after some time, you realize that the tea or the coffee has gone cold or is at a lower temperature as compared to when you brought it in your room. So what has happened? That cup of coffee or tea has actually exchanged energy, thermal energy, through infrared radiation and conduction convection with the surrounding environment, that is your room. And since the cup of tea was at a higher temperature, it has released its energy towards an area of lower temperature, which is your room under these circumstances, right? So that is how a thermal energy will be transferred, sometimes known as the heat gradient, from a high temperature surface or from a high energy source towards a low energy or low temperature source, right? And this will keep on happening until both of the objects who are exchanging energies are exactly at the same temperature. Okay. And then we understand that regions of equal temperature in thermal equilibrium, this is what we already discussed, that if we have a space, for example, the cup and the room, they will keep on exchanging energy until they reach the same temperature, right? Okay. Common understanding, we already know that. So moving on towards the second part of the course of this chapter, understand the physical property about thermometers, how we make thermometers, and some of the common examples that already exist in your syllabus that you should be familiar with. So first, let's look at the word thermometric property. What do we understand by the word thermometric property? You will encounter this in some of the marking schemes. You will encounter this in your book as well. It may not be mentioned in the course right now in the syllabus, but you will encounter this. So basically, what is thermometric property? The examiner or scientist wanted to exploit or take advantage of any physical property that changes with temperature. So any physical property that is measurable, right? Any physical property that changes due to a change in temperature. So we could make a thermometer out of it. What are the common examples that we've already seen? The first one is very common, that is the liquid in glass, right? So what is the physical property that we're exploiting? That liquid expands or contracts upon heating. So in terms of physical property, this was our physical property. And out of that physical property that is responding to a change in temperature, we have made a thermometer out of it. Now, second thing, one of the common ones is the RTD, the resistance temperature detector. Now, simply constructed out of a resistor, we know that resistors experience change in resistance, their own resistance, if they're exposed to heat or changing temperatures, generally directly proportional, right? So most definitely, over here, what has happened is that we are experiencing a change in a resistance in ohms due to a change in its temperature. Again, one of the physical properties, measurable physical properties. By using a voltmeter and ammeter, we can find out the resistance by using V equals to IR, right? And the third quality is another type of thermometer that we sometimes use is a thermocouple. Now we know from O levels that a thermocouple is basically a thermometer constructed out of two dissimilar metals. What do we mean by dissimilar? For example, it could be a combination of zinc and copper, a combination of copper and some other metal, some other alloy. They are fused together. And what happens is that on that fused junction, most definitely constructed out of two different metals, let's say this is metal 1, this is metal 2, and they are fused at this one end, right? If this fused end is exposed to heat or very low temperatures, it experiences and EMF if connected a voltmeter between the open terminals. So what it actually tries to come down to is that a change in temperature is proportional to the change in EMF that is induced because of this dissimilar metal setup, right? So this equation basically comes down to this fact that E2 minus E1, that is a change in EMF, is equal to K times T2 minus T1. This K would be the constant of proportionality, most definitely, because we are converting this proportionality into an equality. There will be a constant K, right? Now, there are formulas for the first two cases as well. For the liquid in glass and for RTD, we have similar looking formulas. So this one basically was temperature is equal to length at point X minus length at 0 degree centigrade, then length at 100 minus length at 0 degree centigrade multiplied by 100. So if we had a thermometer that looks like this, for example, and it is filled, let's say, with mercury or any other liquid, thermometric liquid, right? So this is the bulb. So this is the starting point. And let's say this is our 0 degree centigrade mark. This is our X degree centigrade, which we want to measure. And let's say this is our 100 degree centigrade mark. So where are these lengths represented? So from the moment the bulb ends to the moment where you see the first temperature, this will be L0, which will be replaced at these points. Then we have the unknown lengths known as Lx, which will be replaced at this point. And then we have most definitely from the ending of the bulb to the point of 100 degrees centigrade, the value of L100. And these are generally given in centimeters, right? So a ratio of length is multiplied by 100. And what is 100? The gap between the minimum and the maximum value that is represented on the thermometer. Now be advised, if for example, in a question, the maximum temperature for that question is given to as, let's say, 90 degrees, then over here you will replace this with 90. So this 100 is coming because there are 100 divisions between L100 and L0. There are 100 divisions from 0 up to 100 degrees centigrade, right? Okay. Now, exactly something similar looking formula is for RTD. That is temperature is equal to R naught, sorry, it will be Rx, resistance at the unknown temperature minus resistance at the 0 degree centigrade point, resistance at 100 minus resistance at 0 multiplied by 100. You will notice that this is exactly the same formula in terms of its values as the liquid in glass thermometer, right? But the only change is that over here we are dealing with changing lengths. We are dealing with changing lengths and their ratio. And over here we're dealing with changing resistances and their ratios. So changing resistances. Now, another way to look at this would be this graph, which is represented in, let's say, over on this axis we have degree centigrade, and over this axis we have resistance in ohms. How the question will be set up is going to look something like this, that there is going to be a 0 degree centigrade mark, and there will be a 100 degree centigrade mark, and this line goes something like this. So we know that at 0, there might be resistance given to you already. Let's say it could be 100, 200, 300. So let's say it's starting at 300. And at 100, a resistance might be given to you. Let's say that is 2000. Okay. Now, be advised that this formula that we've just written down, this formula is for linear systems. Now, this is a linear system, as we can see that it's a straight line, right? So, but in reality, systems may not be linear. It's possible that a thermometer may respond to you something like this. Now, this is a non-linear behavior, or it could be responding like this. Again, this is a non-linear behavior. When there is a non-linear behavior, it makes it difficult for us to mathematically predict what is going to happen at this unknown point. Will it be this value or will it be this value? We don't know, right? So generally in A levels, what they're going to do is tell you that this is a linear system, or the thermometer behaves linearly. That would mean that this is a predictable system. So if you can find out the gradient of this graph by any means, because we have two fixed points at 0 degrees centigrade and at 100 degrees centigrade, since we know them, it becomes a predictable system because I know that it is going to have a ratio or a ratioed value at these 2 points or at these two coordinates, right? Now, what if the system was reversed? For example, if we were dealing with a thermistor with a negative temperature coefficient, right? In that case, you'll have to make an equation of the line, an equation of the system. Then you can use this equation. And we will practice a question in this lesson, which actually behaves in the exact opposite way than this one. In that graph or in that question, the graph is going to go like this with a negative gradient. But no need to worry, we'll be able to handle that question as well, keeping in mind that this is actually the thought process behind it, how to visualize the graph. Okay, so we've looked at the formulas of the respective uh, thermometers, and understanding or memorizing their basic properties is exactly carried from O levels, that they are sensitive, they're supposed to be having high range, they're supposed to have uh, easy accessibility, they should be cheaper, and so on and so forth. You can explore those points online as well. Uh, the second point, so we've covered the first point. The second point is the thermodynamic temperature does not depend on the property of the substance. Basically, he's talking about the fact that Kelvin scale is what we use in physics. And what is the significance for Kelvin scale? The main idea behind this is that we are rejecting degree centigrade and degree Fahrenheit based on this idea that they are designed around physical substances, around limited elements, right? Now, for example, degree centigrade was designed around water, around two fixed points of water. At 0 degrees centigrade, it freezes and becomes ice or a solid. At 100 degrees centigrade, it boils. And in the middle, it stays a liquid. So all three states were explored or were explored easily within this scale. So that is what degree centigrade represents. Now, in terms of physics, this is not a good idea because we don't want to be bound to a scale that is designed only around one substance. Now, what's the problem with that one substance? Now, the issue is that when you talk about it in liquid state, or you talk about it in solid state, or you talk about it in gaseous state, in all these states, there is a possibility that it develops intermolecular forces or intermolecular bonds, and these boiling points and melting points are influenced by external physical factors as well. For example, the atmospheric pressure can change the boiling point of water. So not a very good scale that actually depends on more than one physical factors. So what we wanted to do was make a scale or choose a scale that is beyond any other physical requirement other than the kinetic energy. So the kinetic model of matter suggests that the kinetic energy of atoms of any system is proportional to the temperature. Now, what is this temperature? This is actually the thermodynamic temperature. When we say thermodynamic temperature, we're actually talking about the Kelvin scale, which is the universal scale for temperature physics. So we're talking about the Kelvin scale. And what is the significance of Kelvin scale? It does not depend on the property of substance. It does not matter whether you're talking about, let's say, a gas, liquid, or a solid. It's going to remain the same. The concept remains the same. Plus, the other liberty that we have, the other idea that we have, is that we can absolutely guarantee that this Kelvin scale does not have a negative value. Why? Because at very basic zero scale, we assume that inside the system at an atomic level, the kinetic energy has roughly become zero. And we know that the kinetic energy is representative of the temperature. Plus, the potential energy has become minimum. We will be discussing this potential energy and kinetic energy in the next lesson. That is the first law of thermodynamics. That will be covered in a different lesson, in a different video lecture. In that, we are going to discuss this in detail. And we will, of course, solve a question exploring this idea. What is this? What does this mean? So the importance of Kelvin scale, apart from being positive at all times, is that at 0 Kelvin, irrespective, we are talking about water, we're talking about human body temperatures, we're talking about copper, we're talking about any solid, liquid, or gas substance, we are absolutely sure that this is what has happened with its atomic molecules. This is what is happening inside it, right? So irrespective of the bonds, irrespective of the internal other factors, size of the atom, the concentration, the density, how congested the atoms of that solid are, it gives us the idea exactly how to visualize the temperature of that system, right? So Kelvin scale is unbound by the property of substance. So this is actually what it means by this statement in the syllabus. It does not matter. What matters is the kinetic energy of atoms and potential energy of atoms, irrespective whether you're talking about, let's say, water, let's say copper, let's say plastic, or anything else. Point number three, convert temperatures between, and we are familiar with this in chemistry as well, that we have a very basic and simple equation that actually uses temperature in Kelvin can be found by simply adding temperature in degree centigrade with a value of 273 point. Now in your course, this is 273.15, right? So if in the examination it's given to you, you can do that. Another point on the last lesson, you will see that the talk about the 0 Kelvin. So now we've discussed what 0 Kelvin is, and a 0 Kelvin, the fancier name of 0 Kelvin is absolute zero. Again, we'll discuss this in another video, but I've already given you a hint that at 0 Kelvin, we are assuming that the kinetic energy system is almost zero. Potential energy is never zero, but it is at minimum. Another way to look at this absolute zero is that it is impossible to remove any more energy from the system. You cannot remove any more energy from the system. It is in such a low energy level state that it is not possible to cool it down even further or to reduce its potential energy or kinetic energy any further. You cannot remove energy from it anymore. If you want to do that, you'll first have to add energy to the system to give it at a higher temperature, to bring it to a higher temperature, and then come down to this temperature, to 0 Kelvin again. You can do that at that point, but it defeats the purpose. Then that why would you even try to do that? If you're already at 0 Kelvin, it's just understood that you cannot remove any more energy from the system. It is at its lowest energy state. It cannot offer you any more energy in any format, right? Okay, so this is a question involving RTD, resistance temperature detector. Okay, let's look at this question. As I advised you earlier, that this is a question that is going to be with a negative temperature coefficient, and we can see that at 0 degrees centigrade, it has a higher resistance, and at 100 degrees centigrade, it has a lower resistance. So if I had to draw this graph to make things easy, this would have been something like this, that if this is degree centigrade and this is a resistance in ohms, then this is at 3840 and this is at 190. Okay, so this graph is going to actually start something like this from 0 degrees centigrade and goes up to 100 degrees centigrade. So the graph actually goes something like this. Right? So this is our 100 degree centigrade point, and this is that. Sorry, there's a bit of a mistake over here. Actually, at 0 degrees centigrade, it is supposed to be at this point, and at 100, it is supposed to be at this point. So the graph is going to have a negative gradient like this one. Now, you cannot use the conventional resistance RTD temperature formula that I've just discussed over here. We can't do that because this was designed for a positive temperature coefficient. Like the graph is supposed to go upwards. This is going to be a y is equal to mx plus c equation with a positive gradient. But this one is actually going to have a negative gradient. This already has a negative gradient. So what to do in such a situation? First, you find out the gradient of the system, right? So the gradient would be change in y divided by change in x. So our y-axis is changing from 190 minus 3840, and of course, within a minimum of 100 minus 0. So this comes out as minus 36.5. But look at the units. Be careful about the units. On the upper side, we're dealing with ohms, and on the lower side, denominator, we're dealing with degree centigrade, right? So the units will become ohms per degree centigrade, right? So we have the gradient of this equation. And we're going to now explore the y is equal to mx plus c equation. We know that y-intercept of the system is actually 3840, because at 0 degrees centigrade, which we are going to put at x, and a resistance is being dealt at y-axis, if I put this 0, then y is going to be equal to the y-intercept, which is 3840 already. So by this idea, the equation is actually going to become, writing down the gradient, which is going to be minus 36.5x plus 3840. This becomes my equation for this straight line for the RTD, right? Okay, so since he's going to ask us about the temperature at 2300 degrees centigrade, now this 2300 degrees centigrade is most definitely going to be placed at y, because on the y-axis, sorry, 2300 ohms, at y-axis we're representing the resistance. So let's rewrite the equation over here. So y is equal to minus 36.5x plus 3840. So in place of y, we're going to place 2300 is equal to minus 36.5x plus 3840. Now, once you solve this, you'll realize that the answer that is going to come out for x is going to be 42.19. But since we write down answers in two significant figures, this will be 42. Okay, so please be advised that for a negative temperature coefficient, and notice one more line over here that is mentioned, that varies linearly with temperature. Now, when he says that this is a linear behaving resistor, it is most definitely going to be a straight line, and we can use y is equal to mx plus c to solve the system, right? Okay, and I've also mentioned the year and variant of the question so that you can go back to the marking team and see how they have solved it. They will eventually land into this equation, but they haven't mentioned how they've done it. So I've just explained the procedure, how to do it. The next topic is again from O levels, basically talk about specific heat capacity and latent heat of vaporization and fusion. So what is a specific heat capacity? You can look at the definition from the book. We are just going to discuss the formula. So specific heat capacity is basically MC delta T. Now Q is the energy supplied or required, that is in joules. M is your mass, depending upon kg or grams. It depends on the value of the specific heat capacity, whether it's positive or negative. Okay, so this is specific heat capacity, could be in joules per kg degree centigrade or joules per grams degree centigrade. Be advised, you have to give preference to the unit of specific heat capacity. If the unit is in kgs, you'll have to convert all the masses into kgs. If the unit is in grams, then you'll have to convert all the masses into grams. Similarly, in place of degree centigrade, there can be a Kelvin sign as well. Okay. All right. Did we miss a point in the last slide? No, we've done that. Okay. So delta T will be the change in temperature. We ought to ignore this symbol, change in temperature. Be advised that this is T2 minus T1. There are always going to be two temperatures at this stage or in this formula. Now, what is a specific heat capacity? For example, if I write down a value of 5,000 joules per kg degree centigrade, if I write down a value of 7,200 joules per kg degree centigrade, it means that whatever this object is that we're talking about, 1 kg of that substance requires 5,000 joules of energy if we want to increase its temperature by 1 degree centigrade. For example, if the temperature is 22 degrees centigrade, I want to increase it to 23 degrees centigrade. And if its mass is 1 kg, I'll have to spend 5,000 joules of energy, or I'll have to add 5,000 joules of energy into the box or into that object. Similar idea over here. Over here, I require 7,200 joules for every kg if I want to change its temperature by 1 degree centigrade, right? Okay. So this is heat capacity. How to think about it. Okay, we'll solve some questions regarding this as well. And then we have latent heat of fusion and latent heat of vaporization. Now, both of them are basically the change of state energies. This happens, the latent heat of fusion happens at the melting point of any substance, and the vaporization happens at the boiling point of that substance. And both of them are going to have a formula similar in shape, but different variables. So this is going to be MLF, latent heat of fusion, multiplied by mass, and this will be MLV, latent heat of fusion or vaporization, multiplied by mass. And most definitely, this will also be equal to Q is equal to MLF, and Q being the energy requirement. Okay. Now, these two will be required at the melting points or the boiling points of the substances. These are the energy of change of state. Q is equal to MC delta T is actually the energy of change of temperature when you're moving from one temperature to another within the same state. For example, gas remains a gas. Comparison will be with a low temperature with a high temperature or high temperature with a low temperature. So we're not changing the state, we're changing the temperature. So there are only two formulas that you're going to need. Q is equal to mc delta theta and Q is equal to mlf or mlv, depending upon the situation. We're going to look at both of them in the next example. So in this question, it tells me that there is a cup. We have a cup of water, right? So it already has 95 grams of water at 28 degrees centigrade. And what we're going to do now is add 12 grams of ice into it, in the water. Now, ice is at 0 degrees centigrade when it is added into the water. Okay, so it tells you that it is stirred until all the ice melts. Now, first identify that there is actually a change of state over here because ice melts and becomes water. So I'll have to use Q is equal to MLF or MLV depending upon the situation, one way or the other. It's going to ask me about the fact that what is the final temperature of the system. Calculate the final temperature of the water. So how to proceed with such a question? You always start with the law of conservation of energy, that the energy given will be equal to the energy provided or absorbed. So energy is being absorbed by ice because it's at a colder temperature. It will absorb, so the rest of the thermal temperature will reduce and is going to be equal to the energy released by water at a higher temperature, which is at 28 degrees centigrade right now, right? On the other hand, we're going to draw a temperature scale. Let's say this is at 28 degrees centigrade. This is at 0 degrees centigrade, but water. And this is at 0 degrees centigrade, but ice, right? So what's basically going to happen is that ice is going to gain some energy and become water. And since this is a change of state, this will be ml. And since this is solid to liquid or liquid to gas or liquid to solid, this will be fusion, mlf. And then again, it keeps on rising till it settles down to a temperature T somewhere in the middle between 0 and 28. Okay. And then the water that is at 28 degrees centigrade also falls down at a temperature or a common temperature of T, which is our target, which is what we want to find out. Okay. So we'll have mc delta T for ice and mc delta T for water. Now, ice has done two things at the same time. First, it has experienced an absorption of energy to become ice, to become water from ice, right? So it has to melt first by absorbing energy. And we know that when there is a change of state, the temperature does not change. So it's 0 degrees centigrade, 0 degrees centigrade. So I cannot use the formula K is equal to mc delta T because there is no delta T, there is no change of state. So I'm only left with the formula of change of state. So the energy absorbed by ice first is going to be mlf, to the energy absorbed for the change of state. Then when all of the ice has become water eventually at 0 degrees centigrade, that 12 grams of water, the 12 grams of ice at 0 degrees centigrade has now become a part of the water while it is being stirred, while it is being mixed. So that ice of 12 grams has now become water at 12 grams, but at 0 degrees centigrade. Now, since that cold water is being mixed with hot water at 28 degrees centigrade, still that is colder than the 28 degrees centigrade water. So it is still going to be absorbing energy. So we will be adding an mc delta T factor over here because ice water is still absorbing energy, which is going to be equal to the energy released by the hotter water at 28 degrees centigrade. And since we know that water is still at 28, it would be a liquid. There is no change in state involved. That ice has not been able to freeze other liquid molecules from the structure. There is no change of state involved. So energy absorbers have been equal to the energy providers. Now we just simply replace the values, but intelligently. So we have, the equation is going to be a bit long. We'll have to perform the arithmetic correctly, arithmetic operation. So mass of ice, since we're dealing on this side with ice, it will be 12 divided by 1000. Why are we dividing with 1000? Because all of the factors have joules per kg and joules per kg. So all the masses have to be converted into kilograms. So LF fusion, latent heat of fusion, has been given as 3.3 power 6 plus 12 divided by 1000 into C of water is 4200, which is given at this point. So 4200 into change of temperature. Now water has to go from 0 to that final temperature. So it will be T minus 0. So we are simply writing down T. On the other hand, we have water that has to release this energy to eventually heat up ice. So we will have 95 divided by 1000. Again, for the rest of the factors, because everything is in kg, then 4200, and then the delta T factor, which is going to be T minus 28. Sorry, 28 minus T, that would be 28 minus T. So the logic behind is that we want to keep all the energy exchanges positive. We don't want to involve the negative sign. That's why we are subtracting a larger temperature, which is 28, with a smaller temperature, that is T. We understand that this is going to be cooled down because of the ice. So the temperature, final temperature, will most definitely be less than 28. It can't be greater than 28. Just to keep everything positive, mathematically speaking, we are going to write this equation in this way. When you finally solve this, you'll find the temperature, final temperature, will be at 16 degrees centigrade. So adding ice to the glass of water has most definitely reduced its temperature from 28 to 16 degrees centigrade. But what the students generally miss is this idea of change of state. What they generally do is equate simply the water to water. Cold water mixed with hot water. They forget about the fact that ice also requires energy for the change of state. So some of the energy will be taken up by that, right? Okay, next question regarding the heat capacity concept again. So in this one, they are going to involve power of the electric heater. So power is given, time is given, we have the initial temperature, we have the heat capacity, specific heat capacity, we have the mass. He wants us to show that the final temperature is 80 degrees centigrade. Very easy question. Let's look at this. So the formula that we've already done is Q equals to MC delta T. Okay. I'm going to solve it in two ways so that we understand the words that he uses in the examination to avoid confusion. Okay. Now Q is energy. Now this energy is being provided by heater, by a heating element, right? Now this is power and time. We know that power is equal to energy divided by time. Let's take time over there. We get energy is equal to PT, power multiplied by time. Power is in 95 watts multiplied by 6 minutes multiplied by 60 seconds. We know that the unit of power, that is watts, is basically joules per second. So time has to be converted into seconds. So in both of them, in place of Q, the energy supplied, I'll have to replace 95 into 6 into 60 because the energy is coming from the heater. So 95 into 6 into 60 is equal to the rest of the equation. We know that the mass of the system is given to us as 670 grams, and since we're dealing with joules per gram again, we'll have to convert this into kg by dividing with 1000. Similarly, on this side, 670 divided by 1000. And then we are going to have the heat capacity, which is 910. Simply put 910, no problems here. But now there are going to be two ways to solve it. First, we understand that this is delta T, change in temperature. And if I go back to the delta T concept, we understand that delta T is supposed to be a difference of two temperatures, right? So over here, since we are going to be dealing with a higher temperature, so I can write down this T minus 24, which is this one, okay? Or I can simply write down change in temperature as it is. What's going to happen is that over here, when you're going to solve it algebraically, this 24 is going to go to the other side of the equation and get added to the value that you're going to find out, eventually leading to the value of T being equal to 80 degrees centigrade, right? This is one way of looking at it. Now, when you solve it this way around by finding the change in temperature, you'll realize that your answer of change in temperature will come out as 56 degrees centigrade, right? Now, this change means that in reference to 24, there has been an addition of 56 degrees centigrade, ultimately leading you to the final answer, which is 80 degrees centigrade, right? So you could have looked at it from the perspective of change, or you could have looked at it from the perspective of change mathematically put into this equation, right? That is all for today.